Quite Science Journeys. Tonight we are looking at the JWST little red dots, tiny red points seen by the James Webb Space Telescope in the early universe. Small red and not what they seem. At first glance they look ordinary, but they turn out to be young black holes growing at an extraordinary pace hidden inside thick cocoons of gas. By the end of this story you will understand three things: why these objects look so small, why they appear so deeply red, and why they help explain how supermassive black holes began forming so early in cosmic history. Let's begin with what James Webb actually sees. In one of its deepest images, the background is almost completely dark. Most galaxies appear as faint smudges stretched thin by distance and time, and scattered among them are tiny red dots easy to overlook, easy to mistake for something ordinary. For many years, an object like this would have been labelled a small distant galaxy. In the cosmic dawn, that made sense. The early universe was full of small galaxies. Dust was common. Light that travelled for billions of years often arrived looking red. But these little red dots behave differently. Their light is far too concentrated for their size. It does not spread out the way starlight usually does. Instead, it seems to come from a very compact region, as if all the energy were being released from a single tight core. James Webb allows astronomers to look beyond appearance. It does not just record brightness, it shows the shape of the light across wavelengths. And when these red dots are examined that way, their light does not match a galaxy filled with stars. This is not the steady glow of nuclear fusion. It is energy produced as matter falls inward, releasing heat and radiation as it spirals deeper. That energy does not escape freely. It is trapped by thick clouds of gas and dust, absorbed, reshaped and finally released again, mostly as infrared light. That process is what gives these objects their deep red colour. It is also why they appear smaller than expected. Much of what is happening inside is hidden from view. At the centre of each of these red dots is not a quiet cluster of stars. It is a young black hole, not yet supermassive but feeding rapidly, growing fast while still wrapped in the dense material that formed around it in the early universe. This story will move in three simple steps. First, why these objects were so easy to mistake for small galaxies. Second, what James Webb measured that broke that picture. And third, the single physical process that explains what we're seeing: a young black hole, a thick gas cocoon and light transformed as it escapes. What looks small and faint in these images is not empty or insignificant. It is one of the fastest growing structures in the young universe, caught in a brief stage that had long been predicted but never clearly observed before. In the earliest images of the young universe, almost everything appears small. Galaxies had not yet had time to grow. They had not merged, stretched, or settled into the large structures we see today. So when astronomers saw a small object at a great distance, the natural assumption was simple. It was likely a small galaxy, a modest collection of stars still early in its life. The red colour of the light did not raise concerns either. In the early universe, red light was common. Light had to travel across immense distances. As space expanded, wavelengths were stretched, and thick dust surrounded many regions where stars were forming, further reddening the light. For many years this picture worked well enough: small, faint red. Those three traits fit neatly with the idea of a young galaxy far away. As a result, these tiny red points did not stand out. They appeared scattered across deep field images. They showed no clear shape, no obvious structure, nothing that demanded special attention. If you were looking at earlier data, there was little reason to pause. There was no clear sign of a powerful central source. They did not resemble the active galaxies astronomers already knew. That absence reinforced the original intuition. If there were no familiar signs of intense energy, then stars were the safest explanation. Many stars, each relatively faint, adding up to a soft glow. This classification was not a mistake. It was a reasonable conclusion based on what could be observed at the time. Earlier telescopes were not sensitive enough in the deep infrared. They could not see clearly through thick layers of dust. They could not break distant light into detailed structures. So the broader picture remained intact. The early universe was filled with small galaxies, some brighter, some dimmer, some redder, some less so. But all of them fit within a familiar category. Still, there was one small detail that quietly unsettled a few researchers. A handful of these red dots were brighter than expected if they were truly just small galaxies. Not dramatically brighter, just slightly too bright. The difference was subtle enough to ignore. It was not large enough to overturn existing models. It was not clear enough to force a new explanation. In science, small mismatches like this are often set aside waiting for better data, and for a long time that is exactly what happened. These little red dots remained classified as small galaxies. They were not treated as a separate population. They were not seen as part of a larger story. The old intuition held firm. Small meant limited, red meant distant, faint meant ordinary. Only when a new way of seeing became possible did that intuition begin to crack. Not because it was entirely wrong, but because it was no longer sufficient to explain what the universe was quietly revealing. What changed was not the universe. What changed was how clearly we could look. James Webb does not simply see farther. It lets faint infrared light speak more clearly. It turns a blur into a pattern. And patterns are what allow astronomers to tell starlight from something else. In the deep infrared, Webb can look through layers of dust that once acted like curtains. Regions that appeared soft and featureless before now reveal internal structure. Light that once blended together can now separate into a clearer signature. When astronomers turn this ability toward the little red dots, the first surprise was not their colour. It was their compactness. Their light was packed into an area far smaller than expected for a galaxy filled with stars. In a normal galaxy, even a small one, starlight spreads out. Thousands or millions of stars contribute each in its own place. The combined glow has a certain texture, a gradual fall-off from the centre. But these objects were different. Their brightness dropped sharply outside a tight core. The energy seemed to come from a single concentrated region, not from a broad population of stars. That was the first crack in the old picture. The second came from how their light behaved across wavelengths. James Webb does not just take a picture. It shows the shape of the light, how the brightness changes across wavelengths. Starlight tends to follow familiar shapes. Its spectrum carries the signatures of many stars at different temperatures. Those patterns are well known, and they have been measured countless times. The little red dots did not match them. Their spectra showed signs of intense energy, but not the kind produced by stellar fusion. Instead of a mix of stellar fingerprints, there were indications of light that had been absorbed and released again. Energy that had interacted with dense material before escaping. This mattered because light changes when it passes through thick gas and dust. High-energy radiation can be blocked. Shorter wavelengths can be trapped. What finally escapes is often shifted toward the infrared. In other words, redness here was not just a sign of distance. It was a sign of processing. As more of these objects were studied, the pattern repeated. Again and again, the light looked too concentrated. Again and again, the spectra refused to line up with a simple galaxy full of stars. At the same time, something else was missing. There was little or no strong emission at wavelengths where unobscured active galaxies usually shine. No obvious X-ray signals, no loud radio signatures. This absence could have been confusing. For years, astronomers had associated powerful energy sources with clear, unmistakable signals. If those signals were missing, the instinct was to rule out extreme explanations. But Webb was revealing a different situation. A source could be powerful and still remain hidden if it were wrapped in enough material. The data began to point toward a scenario that had long existed in theory but had rarely been seen clearly. A compact energy source, heavily obscured, surrounded by dense gas, releasing energy that had to fight its way out. As this picture came together, estimates of size and mass also began to shift. If the light was coming from a tight core rather than an extended galaxy, then earlier mass estimates were too high. These objects were not enormous galaxies after all. They were smaller, much smaller, and yet their energy output remained striking. For something so compact, the amount of power being released was unusually high. That combination, small size and strong emission, is difficult to explain with stars alone. At this point, the old intuition no longer held. Small no longer meant simple. Red no longer meant distant starlight. Faint no longer meant unimportant. What James Webb had measured forced a change in perspective. These were not ordinary galaxies seen at extreme distance. They were something more focused, more intense, and more deeply hidden. Importantly, this shift did not come from a single dramatic image. It came from consistency, from the same features appearing across many objects, from patterns repeating in independent observations. Trust in science does not grow from surprise alone. It grows from agreement, from different measurements pointing toward the same explanation. By the time this dataset was assembled, the question was no longer whether the old picture was incomplete. That much was clear. The question had become what kind of object could produce exactly this combination of traits. Something compact, something powerful, something young, and something still wrapped in the material that fed it. That is where the story now turns, away from what these objects look like and toward what they contain. If you enjoy calm science stories like this, you can subscribe to Quiet Science Journeys. Each episode explores one vast idea with real observations slowly and clearly, so the strange parts of the universe start to make sense. Now let us slow the pace again, because this hidden phase is where the larger story begins. What could sit inside a tiny red dot and shape its light so completely? The simplest answer is not a new kind of star. It is not a strange new galaxy. It is a familiar engine seen at a very early moment. A black hole, not yet a supermassive black hole like the ones that anchor mature galaxies today, but a young black hole still in its fast growth phase, still surrounded by the material that formed around it in the early universe. A black hole itself does not glow. The glow comes from what falls toward it. Gas in the early universe was abundant. It collected inside young galaxies. It drifted inward under gravity. And when some of that gas approached a black hole, it did not drop straight in. It began to orbit. It formed a disk. It heated up through friction and compression, and that heat became radiation. This is one of the most efficient ways the universe turns gravity into light. Matter loses energy as it spirals inward. The lost energy does not disappear. It comes out as brightness. If you could see that process without obstruction, it would not look like a tiny red dot. It would look like a bright active nucleus, a compact energetic source often visible across many wavelengths. But the early universe rarely offered clean views. Around these young black holes there was thick gas and dust, not a thin haze, a dense cocoon. This cocoon changes everything we observe. High-energy light is the easiest to block. Ultraviolet and X-rays collide with the surrounding material and get absorbed. The radiation heats the cocoon instead of escaping into space. Then the cocoon does something simple and powerful. It gives the energy back, but not in the same form. Hot gas and dust release that absorbed energy again at longer wavelengths. Infrared light, redder light, light that can slip out more easily than the original high-energy radiation. So the object becomes red not only because it is distant, but because its light has been transformed on the way out. This also explains why the light looks so concentrated. The source of the energy is compact. It is centered near the black hole, and the cocoon is compact as well, wrapped tightly around that central region. A galaxy full of stars spreads its light across space, but an accreting black hole releases much of its power from a small region. Even when that power is filtered and softened by the cocoon, it still begins in a tight core. That is why these little red dots do not look like normal galaxies. They are not dominated by starlight. They are dominated by a central engine hidden, muffled, and reshaped. In this picture, the red color is almost like a signature, not a label for distance alone, a sign that energy has been absorbed and released again, and the small appearance is also part of the signature. A compact source wrapped in compact material seen from very far away. Once you accept this, a larger story starts to come into focus. These objects do not need to begin as enormous black holes. They can begin smaller. They can spend time in a buried phase, feeding rapidly while surrounded by dense gas. And during that phase, much of their light is hidden from the wavelengths we used to rely on. That is why earlier surveys could miss them. Not because they were rare, but because they were veiled. This is where the little red dots become more than a curiosity. They begin to look like a missing stage, a stage between a black hole seed and a fully visible quasar, a stage when growth is intense but visibility is limited, a stage when the universe is building mass faster than it is releasing a clean signal. The smallest points in the image can be among the fastest growing structures in the young universe, not because they are quiet, but because their power is being processed, filtered, and softened as it escapes. And now the red dot in the deep field can be seen for what it is, not a tiny calm galaxy, but a young black hole feeding quickly inside a thick cocoon of gas, turning raw gravity into red light. This is the part of the story that matters most. For many years, one question has lingered at the center of cosmology. How did supermassive black holes grow so large so quickly in the early universe? We see quasars less than 1 billion years after the Big Bang. Their black holes already weigh millions or billions of times the mass of the Sun. That seemed difficult to explain. One option was that black holes formed already large. Another was that they grew at extreme rates close to physical limits without interruption. Both ideas carried problems. The little red dots offer a quieter solution. They suggest that early black hole growth did not need to be dramatic or fully exposed. It could happen while hidden, while wrapped in gas, while much of the energy was absorbed and reshaped before escaping. In this picture, a black hole does not need to announce itself immediately as a bright quasar. It can grow steadily in a buried phase, feeding efficiently, building mass, remaining difficult to detect with older instruments. This hidden stage fills an important gap. Before, astronomers could see black hole seeds only in theory, and they could see mature quasars clearly. But the long stretch between those two phases was mostly invisible. The little red dots appear to occupy that middle ground. They are not seeds anymore. They are not yet dominant quasars. They are black holes in the process of becoming something much larger. This also reshapes how we think about early galaxies. If young black holes grew while buried inside dense gas, then galaxies and black holes likely evolved together from the start. The same gas that formed stars also fed the central black hole. Growth happened side by side, not in separate stages. This explains why black holes and galaxies appear so closely linked today. Their histories were intertwined from the beginning. What James Webb has revealed is not a new rule of physics. It is a missing chapter. A chapter where growth was real but visibility was limited. Where the universe was building mass faster than it was releasing clear light. Return once more to the deep field image and to the JWST little red dots within it. A dark background. Faint galaxies stretched thin by distance. And among them a tiny red dot. It no longer looks ordinary. It is not simply a small galaxy far away. It is a young black hole in its most intense phase of growth, still wrapped in the gas that feeds it, still shaping its light before it escapes. What we are seeing is brief. This cocoon stage does not last forever. Eventually the surrounding material thins. The black hole becomes exposed. The light grows brighter and cleaner. But for a short time, the universe hides its most rapid growth behind dust and gas. James Webb was built to see through that veil, not by force, but by patience, by collecting the faint infrared light that older telescopes could not reach. The little red dots remind us that the universe does not always grow in the open. Some of its most important changes happen quietly, partially hidden, waiting for the right way of looking. What appears small and faint can carry enormous significance, not because it is mysterious, but because it shows us how the universe truly builds itself step by step, long before the larger structures come into view.